Okay, for people joining this live stream, we are talking about multi-computation and Wolfram language. And Nick has some new things he's done, which he was going to show off. So I think actually I should set to save this in an appropriate place here. Excuse me. Where was this being saved? Is this being saved in the research?
Yes.
Okay. Is
it and SW notes at the bottom, near the bottom.
Okay. All right. So let's start off. So this is hypergraph multi. Okay. So this is the state and this is the rules. Is that right?
Yeah. So the plan today, I think, is mostly to revisit multi-way system with some fresh perspective on it.
Okay.
So the first idea is just why not just compile everything into hypergraphs, because it makes much easier to say draw some causality from it, arguments.
It's an interesting idea. Okay, we thought we had tree-like expressions, but actually we have hypergraphs. Is that your basic claim?
Yeah. That idea already was explored by Max, I think, a long time ago. Like running Wolfram language as hypergraph writing.
Right. No, he had a compilation to that.
Yeah. So this is basically the same idea, but you can also rewrite expression strings, graphs, trees. We now have trees, and even hypergraphs you can write in this type of hypergraph.
Okay, so let me get used to this idea for a second. Okay, so tree structured expressions have been, your basic claim is when you go to multi-computation, a tree structured symbolic expression is no longer a natural data structure. Instead, hypergraphs are a natural data structure. Is that the basic claim?
Yeah, and the structure of the hypergraph are very computer sciencey. This structure is like the idea is that every hypergraph, hyperedge have a link. Like you can think of it that it have a place in memory. You allocate a place for a hyperedge, and the hyperedge contains links that link to other hyperedges.
Yes.
And that's it. And the replacement of hyperedges is just removing some links, creating some new ones, and that's all what's happening.
Right. Which is essentially what we're doing. I mean, when we deal with symbolic expressions with a symbol tape, well, symbolic expressions are like that, but they have more structure to them. Whereas here you're saying this is a pure, everything is like not a linked list, but a linked hypergraph, basically.
Right.
It's pure link realignment. That the
you can compile a tree into link hypergraph. Each node gonna link to each children.
Yes. Okay, so let's take a look at what you've got here. So this is now. So what are you actually doing here? I see. So what you're doing here is your compiler. Your core data structure is now a hypergraph, and so your string the string here is being compiled into a hypergraph element.
Yeah. So the idea is just compile multi-object here is just it acts only as some kind of storage for rules, and that's it. As soon as you make a rule, it's a simple rule. You can use it in whatever framework we have. You can use it in token-length graphs. You can use it in nest graphs. So principle is not necessarily needed here.
Can I ask what does the 1A0 mean?
It's turning a character string into a linked hypergraph.
Yeah. So the first vertex in the hyperedge is the address of this hyperedge. Then what follows? It's payload, and then any amount of links.
I will demonstrate here by doing this.
So it's a path graph, and it has 1 as like its starting endpoint and 0 is its ending endpoint or something like that.
Yeah, when it's a string, it's a path graph or a list. You can compile a list or string into this kind of simple link hypergraph. But you also can compile any tree.
Right.
So the characters in the string are like edge tags.
That is correct.
Okay.
Right. So the middle element in this hyperedge is the payload.
Right.
But it wouldn't have to be a payload there. That could be, in the case of space, these are just, well, I mean, the thing that's complicated there is that the interpretation of these UUIDs is atoms of space.
Yeah.
And are these always triples?
It's a triple when you have a simple list, but when you have an expression and it has more than one child, it can have more than one link that it links to.
Okay. So it's a hypergraph with general. It's not necessarily a ternary hypergraph.
No, it's like minimal. It's minimal is 2 when you have just an address and a payload. Or you can just ignore the payload, then in principle also allowed.
Right. Okay, so let's walk through this a bit. So what you're saying is this has now been compiled into pure hypergraph transformations, and then this is also a hypergraph transformation. Do you have a function that shows the hypergraph transformation here?
Yeah, I have just a to-link hypergraph function that does every transformation. You can feed any type, and it will make a hypergraph. It can be a rule, just a single rule. I don't think I did it with lists. No. Now treat this as a list, so just give it a single rule.
Okay. So by the way, I mean, that would fit into
yeah. Maybe each individual one.
Wait, sorry, just for some context, I mean, is the idea that this is how it would evaluate arbitrary, Mathematica code, or is this just for? I'm not sure totally what this is for.
This is arbitrary code. I mean, this is the idea is that just as we normally have an evaluator that's based on tree walking, why is this not?
But it seems a little crazy to use to represent it. I mean, like, right. I mean, it seems like this is a vastly less, at least space efficient way of representing expressions, and it's not even going to be easy. Functions like, I don't know, string reverse won't just innately work, will they? Unless it has to reconstruct the string from this hypergraph, which seems really expensive.
Yeah, I mean, this is, look, there's no compiler for this yet, I assume, unless Nick is going to pull a giant elephantine rabbit out of the hat. I mean, this is a thing where the functions it's going to support are things like /dot replacement.
But so is this basically a replacement of, for example, the replacement systems, the string substitution systems that were in multi-way system, or is this also a replacement for the multi-function we saw the other day, which worked with arbitrary code?
And it falls on the same category. As soon as you compile everything to hypergraph, and you're given any hypergraph rewriting rule, you can apply it to it. That's all what it does. It's a very inefficient implementation, like you have an explicit addresses, but I presume that's actually how expressions are stored. So in principle, we could have a data structure.
Sure.
Well, but expressions even, I mean, I just think it seems like this is a fine thing to do for the more abstract, string substitution systems, cellular automata, maybe, et cetera. But that, if you're doing it for arbitrary code, it's going to be just hopelessly inefficient. And efficiency matters because, of course, if you have an arbitrary program and you want to do this sort of non-deterministic evaluation, that's a very expensive operation. And if it's going to be running 10,000 times slower because it's representing expressions in some hypergraph thing that's done in the top level, then it's going to be hopeless.
Hold on, you're making various assumptions here. Okay, first point is, the first thing, the principal thing that we're trying to achieve here is to understand a new style of computation, different from our tree-based, fixed point-based, single-way evaluation. That's the first point. So even if this is not in other words, we don't expect necessarily that this will align, what this is good at will necessarily align with what our existing technology is good at.
Well,
Point one. Yeah.
Well, no, but hold on. Look, there are two uses of this stuff. There is sort of studying kind of simple models like cellular automata, like string substitution systems, like hypergraph substitution systems, etc. And then there's the programming, actual sort of programming version, which is what we talked about a bit more like last time,
Yes.
which was using multi, which sort of inherits a bunch of the built-in deterministic functions, but then it puts sort of non-determinism on top of them, right? These are two different things. This seems fine for the first case of simple models of non-deterministic computation. It seems impossible for the second case.
Okay, the thing is, during the last meeting, the first design objective that we discussed was reproduce useful functionality of multi-way system and its many variants with multi. The problem was, it was difficult to fully understand what we could do with multi. We needed some way to actually be able to explore this functionality. Stephen was giving various examples of what we could do, but it was difficult because we didn't have any way of actually doing it in a clean, kind of consistent way. And what Stephen said was, just go and try and find a way to do it. It can be inefficient. We just need to be able to have some sort of way to discuss this in a more precise way. So that's what we have. So why don't we just look at what Nick did?
Yeah, we should do that.
Before we speak to its
setting a little bit more
limitations,
general
so to speak.
context, okay? To me, even having a framework that allows us to unify all of those different multi-way system functions is useful. The second point is the things that Prolog and the logic programming world and all that kind of thing has traditionally been used for, the cases where people say, look, it's a wonderful solution for this. If we can get those as well, that's a style of programming that's interesting. Moving from that to, and we take, it's like people saying, as they did in the 1990s and things, I'm going to take your arbitrary piece of Fortran code, or actually it was the 80s, and I'm going to parallelize it magically. There's a small amount you can do that, and there's a lot that's super hard. I don't think that's what we're, to give an extreme analogy, the connection machine computer, which was a 4-bit processor computer with no notion of numbers even. There was, its original thing was, oh, look at all the interesting computations you can do on it. And then somebody said, oh, but it has to be able to run Fortran code. And then it was hopeless.
Right.
So
I think this is a perfectly fine thing as basically a wrap up of all the multi-way functions and also generalization of them. Right. That makes perfect sense. I'm just saying this is also, it's not even, I don't think this is really targeting the second use case, which maybe have a totally separate implementation, but that is what we were talking about for the last few weeks. And this is a different thing. So I'm just trying to understand that.
I think that is for now correct, but we may learn things from this that are super useful for the other thing. So
let's look at what Nick has done.
Yes. Let's look at what's happened here. Okay. So the basic concept, and which I really like, is to clarify what has been quite muddy, which is what is a causal relationship, what is a, in the language of what is an atom of existence, what is an eem, which is you're clarifying here. It's, in the case of a string, it's not completely clear what the eames actually are, and you're, I think, clarifying that. Is that a fair characterization, Nick?
Well, for string causal computation was kind of tricky because when you're doing the string replacement, you're moving all the right-hand side of your string, right? So in order to actually compute what was actually caused by what, you have to rerun your computation from beginning rather than just storing some what was destroyed.
But whereas for you, every element here is an atom of existence. And it's very clear which atom affects which other thing. Is that a fair statement?
Yeah, it's like an address in memory. You either store it somewhere, you create it and destroy it.
Right. But put in a more physicsy way, it's kind of like an atom of existence.
Yeah.
These are eames. They have some kind of coordinate where you can understand how they fit together, so to speak.
Yeah, right. And the payload itself also can be like canonicalized into the same structure.
Oh, okay. Okay.
So every hypergraph has a canonical version.
But this could just be in a symbol table. This literal B could just be a shared B in a symbol table, effectively. Is that what you're saying?
It's the same atom of space that every hyperedge links to the same B.
Right. Okay. Let's take a look at what's happening here. Okay. So what's happening? So you say.
So this is just you can just run it multiple times, right? It's just a simple evaluation that the multiple can do if you just have a rule inside of it. Just run it 4 times, you get new hypergraphs. It's like your branchial hypersurface.
Mm-hmm.
And that's it.
Okay.
Multi here is just for storing the rule. You can done it with anything.
Wait a minute, you've got an initial condition as well.
Yeah, initial condition and the rule and some other stuff. It's just a container for your computation.
Right, but it didn't actually do anything yet.
Yeah. And then when you ask for a graph, I use graph here as another data structure, mostly like that all contains all the computation already in its tags. It's like all the tags in this graph contains all the information that happened, an actual event information.
All this graph contains in. What do you mean its tags? In.
Like every edge here, it's like the point is here that the multi-way system itself, if you don't do any equivalence of states, it's just a tree.
Mm-hmm.
That's what I'm like showing later. You're just converting a multi-way system, even when some mergers happened accidentally by just same queue, you still treat it as a tree. So each event is like a single piece of rewriting, whether it's like happened in a completely different path or a different space. It's just a single rewrite. So you have like the same number of events as this number of states.
Okay.
Right? Because it's a tree.
Yep.
And when you
go ahead.
Yeah. So and graph just acts as a data structure of evolution. You can turn it into a tree if you want, and then you can all other notions of graph that we have can be computed from those graphs or trees. It's like branchial graph is like another perspective of it. Instead of looking at it as just some ancestral connections between states, you just pick any children and just turn them into a complete graph, right?
I didn't understand that part. So
wait. Before doing any equivalency, if you don't have a notion of equivalency between states yet,
yes,
the branchial graph is just a union of some complete graphs.
Yes, indeed.
And the union is between children. So the branchial graph, you can do it for every tree, basically, right?
Yes. That's
and then you apply your equivalency with simple like replace function. Like I think I have it later. If you scroll down.
So the edges in the branchial graph are edges between siblings in the tree?
It's like the children. Each node has some amount of children, and you just put those children in a complete graph.
Right.
Branchial graphs just link vertices that in the original graph have a common ancestor, direct ancestor.
Yeah. Which is what you're saying, Ian. They're the siblings of a given parent.
You're right. Yep.
Showing the sibling edges instead of ancestor edges.
Right. So these things here would be in a complete graph together. Right. And then when there's equivalencing, what's going to happen is that a bunch of nodes that were separate in the branchial graph will then kind of glue together.
Right.
Okay, what is this creature?
This is when you glue the initial multi-way graph. If you glue it by equivalencing states, by canonicalizing the hypergraph, for example.
I see. By canonicalizing the hypergraph, we mean there are atoms of space here which are different, but the hypergraph that is formed from that is isomorphic.
Yeah. Right.
Which is a criterion for the observer so to speak, that's an observer-dependent thing, that the observer is equivalencing to identical hypergraphs, even though they're made of different atoms of space.
Yeah.
Okay. So that's this case where your equivalencing function is were the hypergraphs and their literals, so to speak, equivalent, right? And here what you've done looks like you've canonicalized the hypergraph to just use 1, 2, 3, 4, etc., instead of using the UUIDs.
Yeah, it looks like much simpler.
Right.
It's what we have already in the WFR functions. You just ignore the payload to make it more clear, but canonicalize every addresses to make it.
Yes. No, that's what you're doing. That's the graph canonicalization. This is essentially making an index graph. It's like an index hypergraph. Is that right?
Yeah, it's a little bit more tricky than that. You have to there's a canonical order of hyperedges, so that it's like no matter how you permute every hyperedge and how you rename all the atoms, it's still gonna be canonicalized into the same way.
Right. Right. Okay, so this is what our usual multi-way graph would give. Although I don't know what these different colors mean.
It's just a rule ID because we have two rules.
I see, which is something we should
we
have had
have
in a multi-way system long ago. Yeah.
So we have two kinds of edges,
That's nice.
two kinds of events.
Right.
But we don't deduplicate any events, so the same number of events that we had.
Right. Right. Okay.
And here we're also not deduplicating anything. It's still the same number of edges that we had when we had just complete graphs. I think it's like have much more information. And the causal graphs are the most challenging. So you can like just look at the tooltip for each event in the causal graph.
Why is the event labeled by a string like that?
I'm labeling it by just output string. I have an initial event, and it's just an output of an event.
So what we've done previously with strings is we've labeled it by a double-decker thing, which is the input string on top of the output string.
Yeah, it wouldn't work in general, so I just picked this representation for now. It works for any kind, like for strings, expressions.
To just label an event by its output.
Yeah, I think it's enough. Because we have the same number of events and states if you form a graph from a multi-way system.
Wait a minute. Go ahead, but this is, so in the token event graph view of this, which maybe you're going to get to, the tokens here are always the hyperedges.
Yeah.
And then the events, in this case, will be that one consumes two tokens to generate two tokens. But maybe you're going to show that picture.
Yeah, I think I have something later.
What is the transitive reduction? What's the interpretation of the transitive reduction?
I think that's what we usually do by default. We not show the original causal graph also.
Yeah, you're right. You're right. We show the transitive reduction. Okay. Token event graph. Okay, I'm confused by why this has a tripartite as opposed to a bipartite creature.
Because it also includes the states. It's more like a local multi-way system now. Because I've made a modification to token graph when you also can include the states themselves besides the tokens.
Okay, so what's the what's the way that you connect? So I understand how tokens lead into events. Tokens are like chemical reactions. You have some inputs, you have the event, and then you have outputs, right? How do the states relate to that? Because what you have here is you've got these tokens leading to a state, leading to an event. I'm confused by that.
Well,
I thought
what I have there.
Go ahead.
What I have there is like two functions, an additional two functions. How you would, given a state, decompose it into tokens, well, it's usually a simple one. If you have just a list of hyperedges, it's going to be identity. Each hyperedge is a token. And recombination, how would you, given every output token from each event, how you will make a new state from outward?
Yeah, look, I mean, you can see, right? Each of the tokens, they feed into the state. So B, and A feed into BBA, and then BBA undergoes some sort of transformation. I don't understand.
But the transformation is on tokens. It's just it's
I see.
because the recombination function is so general. It can even be, it can combine tokens from different states that was as an input. So it's not really, so it's not clear how you would connect it with that.
Right, but, I mean,
maybe I'll
is,
change that.
So look, I think this is a different kind of edge. The edge that's here, look, I mean, this is the challenge. This is the difference between local and global multi-way systems and so on. Is this thing about, is it a token world, or is it a states-based thing? And those are two different views of what's going on, I think. And I claim it's going to be very difficult to put those into one graph, maybe not. Because like otherwise you're consuming tokens, and that's a well understood thing. Every node, every event node is going to have the same local structure around it. So I'm confused by this picture. Because it seems to me that this is.
Nick, walk me through. So take this BBA state. So you have BBA, and there's an event so there's an event that goes to A, and then that goes to BBBA.
Yeah. That event produced a number of tokens. One of the tokens was A, and then it just recombined with other tokens into a new state. And you show states as global states, that they act on the whole state, even though locally they only involve some number of tokens, not the whole state.
Is it the case that what's happening here is that really, let's see, what was the rule here? I thought the rule was just BB goes to something or other. See, that's the point. I think the rule says was BB goes to something, which I would have expected.
There are two rules. A goes to A, BA. A goes to BA, I think. And another one, BB goes to something else.
Okay, but that event there is that event there is a BB goes to something or other event, is it not? I don't understand what this is doing with the A coming in here. I would have expected the BB goes to an event that then produces.
Well, if you remove the states, that's what you're gonna get.
Okay, so can I?
States are optional.
Okay, how do I do that?
Well, expand the options to the token one graph. So we have state vertices goes to true. Just make it false.
Okay. Okay, so we've got the A goes, so here you haven't shown the different rules in any different distinguished way here. But basically, that's an A goes to AB node, and somewhere we'll have a BB goes to something or other node.
Yeah.
So that's a BB goes to, what the heck is this? Why is there a backward arrow going to the B there?
I think it is because that's of this complicated recombination function, but it means token wasn't involved in the rule. We have a state BBA, right? With maybe a state with 3 Bs, but the event only touched the 2 Bs. So you have to reproduce the one of the Bs that wasn't involved in the rule. So that's what this edge is shown there.
Jonathan's making a comment here, which I don't understand, about cyclicity.
No,
where is the
I was just commenting on exactly the same thing you commented on, which is the fact that you've got the fact that this graph has cycles means that it's difficult to parse.
But it's got cycles because you're somehow reusing a token, or
No,
what?
I understand why it has cycles.
No, but I don't understand why it has cycles.
Because of effectively token idempotence of certain events.
I see.
But in local multi-way system, for instance, we explicitly remove cycles because it's kind of hard to understand if you have them.
I mean, this is called, it's a closed time-like curve because basically nothing changed in the world. It's a trivial closed time-like curve because there was an unchanging, some atom just reproduced itself. All right?
Yes. I think I have an option in the token graph that also removes cycles like that. So it's also optional whether you want them or not.
Okay, fair enough. But let's keep going here. So we're understanding. Okay, so I don't completely understand these state things. I vaguely understand them, and I can't say I completely understand them. But just to frame this, what is this thing? Do you believe this is some combination of global? I mean, that's like global state-based stuff. That's like local multi.
This is supposed to be global. This is supposed to be global.
Okay. I don't know. It's just the only way I found that makes sense to put all of those in one graph. I think I've tried some bunch of stuff and it didn't fit. So when you connect a state, make this graph this tripartite graph: token state event, token state event.
Okay, but so the workflow is there are a bunch of tokens, they combine into a state. See, the thing that's confusing to me is that it's a subpart of that state that's involved in the event, but that's not represented by that edge.
Well, because it's like hidden somehow. Well, you can tag it. All the information is in the tag or in the event itself. What actual tokens will reveal to them.
Look,
and when you remove the state, it's there.
To me, what should be happening in this graph is that whatever it is, BB goes to whatever it is, should just show up as BB goes into this event. Okay? Then there should be a lasso, so to speak, of various tokens that are somehow connected together to be reknitted into a state. But that's a piece of metadata of the token event graph, isn't it? That's saying there's a token event graph and everything is happening based on events to tokens. But somewhere there is also a thing where you're connecting together, sequences of tokens. You're knitting together sequences of tokens that should be considered as states.
But how different is that from a foliation, like a local foliation?
Not very different. It's not very different. It's the same kind of idea.
Right.
Yes, which I think is what, states in a sense. Again, these states are in the eye of the beholder.
Right. So these are like local foliations by which we get these states.
I think so.
From tokens. It's an interesting idea. Okay, I like that.
Okay, let's keep going here because I think something exciting is going to happen. Okay. This is a comment.
Maybe we should discuss the causal graph. I think we haven't.
Okay. All right. Which was
too much time on it. Yeah.
Okay.
It's like how exactly it was constructed. I also want to pay attention to the information that each event has, not just what it was created or destroyed, but it also contains a position in the original multi-way graph. So it's like a branch position of this event. So when you actually draw a conclusion whether two events are causally connected or not, you're not just looking whether the same atom was destroyed that was created by the previous event. You also look whether those events occupy the same path in the multi-way system. Because
why is that relevant? Isn't it? I'm sorry. Isn't causal dependence are the same atoms of existence? Do you depend on an atom of existence that was used somewhere else? Is that not the definition of causality? What else do you need to know in causality?
I think it's like if you if you just have a multiway system, it doesn't make sense to connect two events from independent paths, even though they maybe involve the same atoms of space, because they're completely
I see.
like parallel, right? So they shouldn't be connected. They should be have like one of the three positions should be a prefix of another one in order to make a causal connection. And I think in the original multiway system, that wasn't clear. It's like I had an example when there's some connection that was between those branchily disconnected events, just because it's like they involve the same.
That is a confusing thing. I mean, two branches of history that involve the same atoms. In a sense, that's what entanglement is about, isn't it? That different branches of history can involve the same atoms of existence.
Maybe, yeah. But like this causal graph has all events, has all of this information, so you can post-process it and maybe do something like it. It's like it almost has a complete coordinates, absolute coordinates for each event.
I didn't understand the absolute coordinate idea. So that's in the hypergraph. I mean, so another point is that there is, let's see, I mean, there's a structure that is just the ticker tape of all events that happen. You can just make a list of all the events that happen. There's no notion of ordering. They just like you can make a list of hyperedges in a hypergraph. So similarly, you can just make a list of events, and then there's a knitting together of those events that's defined by the content of the events. Is that the point that you're making?
Yeah, and I'm also making a point that it's not just created and destroyed information, but the original position in the multiway system, whether those are branchily disconnected events or not.
I understand the claim for the initial multiway system. I'm unconvinced that. I mean, I think in the end, that's the story of entanglement. That which is on a different branch of history might still be the same thing.
It might be, but it's not a part of a causal graph connection. It's a
I see.
Part of something else. It's a branchial graph already or something else.
The consequences, I mean, I remember, Nick, you didn't include it in this notebook, but you were showing me an example of a notebook where there was greater, say, causal invariance under the existing approach to making these causal graphs than the approach that
I was
you're
just
taking.
showing the existing multiway system thing.
So as you can see in this example, it's quite ramified, which means if you take this approach, obviously there's going to be much less causal invariance. And so if we adopt this for multicomputation, there are some implications, theoretical implications for making that choice.
Not causal invariance, just the amount of causal connections is going to be drop. Just because you disconnect all the branch events. That's it.
Yes, which I think has a definite physical interpretation, which is not. I mean, that depends on whether the observer, in some sense, spans different branches of history. If you separate, to separate those branches of history is to posit that the observer cannot unify them. Which, okay, let's keep going. Let's see what this structurally does. Okay, so we've now got a combinator.
Right. And it's compiled into this thing. And this is like an explicit hypergraph for each combinator.
That's amusing. And what's the relationship between the combinator tree and the combinator hypergraph?
I think it's almost one-to-one, right? If you just make a combinator tree and compile it into a hypergraph, that's the same thing.
So if I were to look, for example, at, let me just see here.
Is it possible to convert a random tree into a hypergraph?
Sure.
Yeah, let's do it. So let's take a random tree. Do you have a tree converter?
They all call to linked hypergraph.
Okay. Okay, who wants to try to understand this? So we've got a 1. Do you think the 10s are the actual labels here, or the 10s are something different?
The actual
labels get
the
preserved?
second element. The second element is the payload. So
But how did it? But I mean, the infrastructure is a 1. Could you explain that?
one is a address of that
Address.
root, is a address of that 10 node, and then 4 links are followed. So you have to find a hyperedge that starts with a 2. So it's the second hyperedge, and it has 5 as a payload, and it's the first child of the root node.
I think these are the numbers in a top-down depth first traversal.
And then you have link to 4, which is 9.
So if I draw this hypergraph,
Link to 5, which is 7. You have link to 10, which is 1. Okay, I get it.
oh my gosh.
Stephen, can you run that code in chat?
Yeah. Except that I hate the naked variable there, but oops.
And actually, you'll have to specify tree traversal order. Top down.
Oh, top down.
Mhm.
I'm sorry, I have to do this. Okay, so now what is this going to tell us? This is
I think those are the indices that 2 linked.
1, 2, 3, 4. 1 has a payload and 4 children.
Mhm.
2 has oh, I see. We have to compare that with this here, where that was a 5, has payload 5 and 1 child.
3.
Okay. Okay. So this is now the folded up version of this. Is that right? What's the relationship between this? Nick, what the numbers here are these index numbers, right?
And sometimes
No.
it's a payload because actually,
Can we distinguish
for-
the payload and the index numbers? Could we make a
Yeah.
tree where Ian, could
You
I
can
make
just
this
map it.
random? What's that?
you can just map it all to all the second elements in each hyperedge, map it with hold form or something. in
Do
order to
tree map of
distinguish.
2 string or integer name or something.
I would just make a hold form
Okay,
around
just tell me
each
what-
second element.
and
Map
what-
for this hypergraph, you do map at hold form, give it a hypergraph, and list of all, comma 2. And now you do, and now you make a model plot, Wolfram model plot of that.
Oh, I see. That's distinguished. Well, I wish I could see which ones are the. Let me not just do a hold form. I'm going to just do framed here.
Okay.
Okay, so those are the payloads in the actual tree, and these are the infrastructure nodes, basically.
Right.
Okay, so we should be able to read off the tree. 10 goes to, through the infrastructure node, to 5.
I have a like from linked hypergraph. I have a backwards function too. You can give it a hypergraph and make a tree.
Okay. Okay, let's keep going here. Let's try to understand this. Okay, so then you're saying It's a little bit hard to understand, but you're saying that this hypergraph, so what I was looking for, let me just find one. Let's see, what's a nice multi-way system? Just so I understand what's going on here. So this, wherever this was, okay, so before we get to these, those are SK things again. So, okay, so let's just do this. Okay, this is the one. And this claim is that this will make a multi-way graph. So here, I'm just trying to understand the relationship between these things. This thing here should make a terminating multi-way graph. So there it does nothing. Okay. And then what I want to do is I want to compute graph, 5, and I don't know what that thing is doing there.
Just a vertex shape function.
Okay,
Or
I'm
maybe
gonna
something
do it
else.
without a vertex shape function just to understand what it does. Why is it taking so long? That is
Because
not
it can be slow. It can be slow.
okay. All right. Okay, great. So in fact, that picture is encouragingly similar to this picture here. Okay, so that is the correct, that's the multi-way graph of those combinator rewrites. Great. Okay, now let's understand some of these things up here. So those combinator expressions can be compiled into hypergraphs.
Right, yeah.
And then this is something we've never really had for combinators, which is a good causal graph. Is that right? In terms of, go ahead.
The same information as above. Create it, destroy it, and the reposition. And you can draw all the causal connections between events.
Okay, and this is your slightly confusing states and.
Yeah.
Okay, let's see what else happens here. What is this? X plus 1, 2x. So this is numerical multi-way system.
Yep.
And this is showing how the expressions get built up. First as a tree, and then with recombination. All right.
Deduplication.
Also, can we, okay, so you're deduplicating these things which are all equal to 3. That is the canonical version. Is that correct? I mean, those two should be equal. I don't understand why those are showing up as different nodes.
No, they're different brackets. They're parenthesized differently.
Okay.
So they correspond to different hypergraphs.
But one canonicalization would be to just say what's numerical value.
Yeah, for example.
I mean, that's a canonicalization. So I mean, that's an interesting observer thing. Some observers might only pay attention to the numerical value. So, for example, how would I do that? So if I were to do that with, I've got this hypergraph multi. What am I doing here? What are you doing here? Can we get, okay, so now if I do, why is it so slow, by the way?
I'm using just my multi-replace. And because I'm replacing not the hyper edges, it's not just replacing expressions.
I see. So
I mean-
it's having to search the hyper edges every time and things like that.
Yeah, it's like a subset replacement.
Is it
Must use-
using subset replace?
I tried, but it turns out it's rather limited in the way I wanted it to.
In what sense?
It's like the rules that I produce, they contain pattern sequence, and they don't, and it's not supported. It's like in order to be able to replace arbitrary, like arity expressions, you have to make some kind of pattern sequence pattern on the left hand side.
You should complain to Tony about that.
Oh, actually,
could-
meant not the subset replace. I meant the set replace, the actual Wolfram model as a backend.
Oh, okay. Could you use subset replace? Which is, I think, what Jonathan has used. Okay, so this is the unduplicated version. How do I deduplicate?
With that vertex replace, you just do a vertex replace and replace each vertex to some canonical version. Oh,
That's
version
after
you
the
want.
fact. I want to do it.
Yeah.
Can I do it while it's computing so that I converge vertices while it's computing? Yeah.
Well, not really, but you have to modify the rule.
Okay, fine. But I mean, to me, that's an important point in terms of the general theory of multicomputation. That is, multicomputation, in the raw, just generates trees. Multicomputation post-observation has many equivalences that have been conflated together. But for efficiency purposes, you probably want to do those conflations on an ongoing basis, not wait till the end.
Yeah, but you have to record it at least. I think that's important information.
Yes, I know. That's
In
the
order to
tricky part.
And there are different ways to conflate. I mean, in this case of 1 plus 1 plus 1 versus 1 plus 1 plus 1, I mean, in meta mathematics, right, we would say that it really depends on what you have in your entailment cone. If you have some associativity axiom, you're saying that the observer pays attention to the numerical value. But I think what you really mean there is if this was in an entailment cone with associativity, that these would be equated. And that's something that, I mean, just as a slightly tangential remark, I don't think we fully understood is in terms of observer theory. I mean, we have foliations as one example of a choice that observers can make, but I don't think we fully explored exactly all the different, say, choices or kinds of observer constraints that lead to equivalencing. I think it's probably more complicated. Yeah, right.
And what you're describing is in an entailment cone, in an entailment fabric, rather, the mathematician observer has a collection of facts in their bag, so to speak, that they are using to knit together a fabric to, for example, equivalence those different associativity, those different.
Well, yeah, the fabric is going to be composed of the cones, and the cones are going to include axioms, or if we're extending this beyond metamathematics, which is interesting, which we haven't really thought about fully, thinking about fabrics in general for observers, what exactly those cones are, where you're introducing.
Well, look, we know the
Yes,
example for pressure measurement, okay, which is you've got a great big, baffle, paddle, whatever it is, that many molecules are hitting. And we know that the equivalencing we're doing is it doesn't matter where the molecules hit. All that matters is how many of them hit. So that's an analogy to what in mathematics would be an associativity axiom. That's just saying there's an equivalencing of all those different molecular configurations that all just have the same momentum transfer.
Well, that is good food for thought. The idea that the general kind of transductions, like in this case, it's like instrumentation with measurement, these general kind of transductions in observer theory, that we might turn to the case of axioms and axiomatic mathematics as a kind of an analog for how to meta model those. That is interesting. I had not thought about that before.
Yeah, I hadn't either. Jonathan had a comment. Can you say what you were?
No, I was sorry. What you were saying seemed unnecessarily confused. I mean, so in mathematics, the equivalence function is just based on whether or not a branch pair resolves at some point in the future, right? That's the general case of what you were talking about.
It's not unnecessarily confused, because what we're discussing is observer theory, and we're not just discussing it in mathematics. We're discussing it in general, how this applies to multi-computation.
No, but I want to understand what Jonathan just said. So
trust me, I understand the conversation.
Yeah, I mean, Jonathan is making the point that that all these entailment cones and all this kind of thing, one way to say it is, will these ever become equivalent? Like, will these two things, if you have the associativity axiom in your collection of things, that then one statement is, will these ever become equivalent? As opposed to what I was saying was, Jonathan's point is, go ahead.
And the point you were making about the relationship between axioms and what are essentially just coarse grainings in measurement theory is a case of exactly the same phenomenon, right? Your measurement apparatus is a lossy function that essentially sends, many different possible configurations of the universe to a single observable value. And so then again, you're saying that you measure two systems to be in the same state if and only if, subject to that additional set of rules, a given branch pair will resolve at some point in the future.
Exactly. Yes, I agree with that.
Can we just clarify that a second? I agree with that basic comment, but let's take the example of the pressure measurement, where you've got this big paddle thing. Okay. Walk me through what is the function? I understand that in the end, what's going to happen is that there's an attractor that causes all those different microstates to end up in the same total momentum transfer.
Right. So as I say, this is essentially the formal definition of what it means to be a piece of measurement apparatus, right? It's a lossy function on the space of possible states.
Yes, I understand. But you're saying
you could imagine something like, for the case of to construct a minimal example of your pressure case, you could imagine a string substitution system in which every appearance of the A character corresponds to a particular molecule, and then you have a sort of meta rule. It's just a rule, but it's not a rule of specific string to specific string, but rather a string pattern to a string pattern that would just say, map every string with 3 A's in it to the number 3 or something.
Yes.
And then, obviously, again, now your equivalence function just becomes, will a given branch pair converge at some point in the future, given you add that additional axiom to your system.
Okay, so the basic point you're making there is that you're making the claim, an interesting claim, that a good meta model of a measuring apparatus is a pattern transformation rule.
Well, specifically, it has to be a lossy function. Right. If it just sends the space of states to something that's the same size, then you're not performing a measurement.
Yeah, right. But I mean, a typical case, if you say, right. So you're saying, as a minimal model for our measuring device, so that's a way to compile measuring devices, basically. You're saying that the
right, which has already been done in some of the mathematical aspects of the physics project.
Example.
Well, the general compilation of Hermitian operators in quantum information theory to multi-way rules, for instance, which was the topic of, a couple of papers.
Explain. I think I understand, but can you say more explicitly what
Well, in that case, it's really simple what the lossy measurement rule is, right? You've got some branchial graph. Mm-hmm. You add rules that map not, neighboring branchial graphs to neighboring branchial graphs, but rather vertices on the same branchial graph to each other. So now, rather than having unitary transformations that are, reversed under edge flipping, you have Hermitian transformations that remain the same under edge flipping. And that allows you to parameterize an arbitrary, well, at least an arbitrary Hermitian operator, so an arbitrary quantum measurement.
So what do you think, to skip around a little bit, but what do you think for an actual physically implementable measurement, what constraints are there on that transformation rule? Just like we have go ahead.
There are some trivial ones, right? Like one would expect that, for instance, your lossy measurement function can't violate causality, right? So to take again the example, to take the pressure example, you could count A's in a particular substring that's sort of bounded by some light cone, but you couldn't count A's across the global string, for instance.
Yes.
Like
But, I mean,
there's
yeah.
a pretty clear like necessary set of conditions needed to define a physically plausible measurement.
But I think it would be interesting. I mean, so we were starting to look at actual measuring devices and how they actually work, and trying to, see what is the, causality is one constraint, but it's like, what is the analog of computation for measurement, so to speak? What's the analog of the Turing machine?
This is a different project. This is
I
a
know.
different project.
I know it's a different project. I know it's a different project. So I'm just being greedy. If maybe we'll solve that one at the same time as this one. But I think the important point here is that what Nick is revealing is that, which we sort of already knew, is that knowing what it is that you're trying to compute, that computing everything in this tree of possibilities is very computationally, I mean, that is the ultimate N, non-deterministic computation story. But the conflation process is more of an art, because it is more of an, it's more of an observer-dependent art. In other words, what conflation you can do depends on what you final, kind of answers you want to get. If that makes sense. It's not going to be a thing. There's not going to be a general pure algorithmic optimization of these trees. It's going to depend on what kind of observation you want to get out, I believe.
That's right.
Do you agree with that claim? There's no general, in other words, in the end, you're going to coarse grain, you're going to, have a contractive mapping, whatever else it is. But the point is to apply that contractive mapping sort of, during the computation, rather than have to wait to the end. Now, in quantum mechanics, that's actually not how it works, right? In quantum mechanics, the usual assumption is you do what you do inside the system and then you measure it. I mean, I don't know, in modern, okay, this is my ignorance of modern quantum information theory, but are there serious situations in which you have intermediate measurement that is part of the computational process, or is it mostly?
That's the whole basis of like one-way quantum computing, right? Where the measurement is actually doing the computation.
Explain.
Well, so in one-way quantum computing, you prepare a maximally entangled resource state, and so rather than starting off with a sort of pure unentangled thing, and then doing a unitary operation on it, and then applying a Hermitian operator at the end, you start with some maximally entangled thing with a very, very complicated, tensor product structure. And then you just do sort of single qubit or multi-qubit measurements on it. And the application of those Hermitian operators is the performance of your computation. So you get a sort of irreversible version of quantum computation.
Is that, I mean, to what extent is that like a one-way pad in cryptography where you've made this very complicated thing and you're just biting off little pieces of it? Or is it different from that?
I guess it's similar, but I mean, like one-way pads are, I mean, at a high level, the key distinction is that one-way pads are kind of only really of theoretical interest in cryptography, whereas one-way quantum computers are, I mean, there are at least people who claim to have built them.
So how do you make the entangled state?
Physically, I don't know.
Okay, but these Hermitian operators, is it like, could you implement a Turing machine by doing this Hermitian operator, then this one, or is
yes,
it?
exactly. But of course, the key thing about it is that you couldn't, for instance, revisit previous states on the tape.
I see. So in that sense, it's like a one-time pad.
Yeah, right.
That doesn't strike me as being quite, I mean, because what I was wondering was, if we knew enough about the fine structure of it, I mean, okay, so I've been learning a little bit about the actual physics of quantum computers. And there's a lot of weirdness and hokiness there, but that's a different issue. This question of whether you can insert measurement in the middle of the thing and not just blow the whole system up. And what you're saying is, this is an example. You're What did you
But
call it?
I'm not convinced that they are independent questions, right? Because if you imagine chaining together, like a sort of exact sequence in algebra or something, where the output of an ordinary quantum computation now becomes the input of a one-way quantum computation.
Yep.
Then this is more or less the equivalent of a multi-way system where you do merging intermediately rather than just at the end.
Yes, I agree.
But one concern that I have is that for anything that's multi-computationally irreducible, I don't see what trying to make the equivalences during the computation really buys you, as opposed to just doing them after the fact. If you don't know at any given successive step what kind of mergings are possible under some given merging regime, I don't really understand what benefit is afforded by doing it in real time as opposed to post-processing.
Because we live in real time. That is, if we're trying to, if we are trying to replicate things like our experience of nature, saying, let's wait until the end of the universe and see what kind of complicated entangled quantum state was produced, and then our future descendants will read it. That's what you're essentially saying there.
Fine. Okay. So if you want to meta model the observer,
well, and this is also a fundamental question about computation, right? This is the question. What we have done in all the computation that we've done, it's been input to output computation. It has not been intermediately observed computation.
Right.
And again, for the universe, the input to output computation is not the one that we exist in, so to speak.
I get it. So there would be something like, it's almost like having an observer event where it's like between updates, you also have some observation that's being performed on it where it's being coarse grained, and this is just being iterated.
Right. And I think what Nick was doing there in the states recombination is something tantamount to that.
Right.
That is that's like
right.
So I mean,
that's interesting.
Which reminds one of Jonathan's, completion processes for quantum measurement, I think. Does it remind one of that? That somewhere in the middle of this, token event graph, whatever else it is, you do a completion, which is an out of rules. It's a different thing that wasn't directly what was specified by the rules. It was
all you're talking about here is just the idea that, state equivalence functions and coarse grainings are really the same thing, which I think we've known for a while. And it just so happens that completions are a very general way to impose both concepts.
I agree that state equivalence functions and coarse graining, I agree with all of those statements.
Right. So, but are we saying anything new here?
We're trying to clean up the concepts. That's the,
the idea that doing multi-computations and including some way of meta modeling observers where we're actually introducing the coarse grainings, in a way that's endogenous to the computation as it's being run, that's certainly new. This is certainly something I haven't heard being discussed before.
Okay, it is it depends on your definition of newness. And it depends on how much computational irreducibility you allow between the idea and the conclusion.
Certainly the idea of having endogenous coarse grainings in multi-way systems is not, as far as I'm aware, a new idea.
Don't have right now. I mean, we haven't
implemented that except for completions, right? And Jonathan, you've implemented things like this with completions in multi-way systems.
Right, but completions are a general way of imposing canonicalization of states on a branch like hypersurface. I mean, this is the same problem.
So you're saying by completions, you mean,
completions by definition let you impose arbitrary equivalences on states on a given branch like hypersurface, right?
Well, let's unpack that for a second.
Unless you're using some notion of coarse graining that's different from anything.
No, wait a second. A completion takes two branches on a branch pair and can conflate them.
Right.
Now,
or is it another way? It takes two states on a branch like hypersurface and imposes an equivalence relation between them.
Fine, but let's take and then we bring in, we wheel in a measuring apparatus from the next door lab. and it's a different set of, it brings new rules into the system, doesn't it? That are not the same as.
It's possible that the conceptual basis of all of this has changed since I was last involved in these discussions, but a measurement, again, like a measuring apparatus is a lossy function. It's a coarse graining system, right? So it will take a collection of possible states of some system, and it will produce equivalence classes of them that have the same observable value. Right?
Yes.
Yes.
That's just taking a branch-like hypersurface and imposing an arbitrary equivalence relation on it.
Yes.
And completion, the reason for investigating completion was that that's an operational way to do that by just incorporating new rules into the system.
Okay, but if they're arbitrary new rules, I agree with you. If they're new rules that specifically come from branch pairs, that's a more specific case, is it not?
Well, why? Because if you can complete an arbitrary pair of states on a branch-like hypersurface, you can impose an arbitrary equivalence relation between states on a branch-like hypersurface.
I see what you're saying.
There's no content in that.
Your claim is that everything came from the Big Bang eventually, and the question is, and these two things would normally be at completely different places in branch Hill space, and your basic statement is.
But if I can add edges that connect them and make them neighbors, then they don't anymore, and that's what a completion is.
But the meta point there, which was a little different from the way I was thinking about it, is assume everything comes from the Big Bang. So everything is coming from the same place. Then all that you need to do, then everything's going to be on that branch-like hypersurface. And then it's a question of just picking two things and gluing them together. As opposed to the way I was thinking about it, as we were talking about it previously which is there's a kind of a, I mean, you're right that insofar as the things that exist in the world all are all there somewhere. All the things that can exist in the world are somewhere on that branch-like hypersurface. Therefore, all measurement can ever do or coarse graining can ever do is to conflate things in different places on that hypersurface. Therefore, you can always think of that as being something where you are conflating things that branched at some point in the past. I agree.
That's the picture of measurement, at least I've had for the last 3 years or whatever.
There's a certain, I'm now going to be big on this computational irreducibility of ideas. That is, how far do you have to go? I mean, anyway, right.
I would say in relation to the stuff we were discussing right at the beginning about the hypergraph compilation stuff, there is an interesting conversation to be had about using hypergraphs to represent kind of generalizations of expressions that relates to a whole bunch of CT stuff and other things.
Explain. By CT, we unpack that to category theory.
Right. I mean, so for instance, like in the framework that we're currently developing for the handling, say, string diagrams in monoidal categories, those are already like a generalization of ordinary expressions. And then there's the formalism of Kissinger and Fong with hypergraph categories. That's a generalization of that, which eventually I'd like to implement because it's relevant to the categorical quantum mechanics business. And so yeah, that's an even further generalization of what it means to be an expression. And that,
in what sense are you having to generalize the notion of expression for the string diagrams?
Okay, so with an ordinary expression, right? Why is it a tree? Well, it's a tree because your sub-expressions are all effectively many-to-one functions, right? You have, f of xy, so you have xy going into a single value f.
Okay.
Right?
I wouldn't necessarily think of a function that way, but yeah, okay, let's take it as that. Yes. I mean, yeah.
But you could now imagine having a many-valued version of that, right? You have xy goes to f, but f actually produces produces f1 of xy and f2 of xy or something. So right. now you haven't got a tree, you've got a DAG. And that's effectively the structure of an ordinary string diagram, right? So you take some ordinary category with ordinary notions of function composition, and you induce a tensor product structure that lets you chain together that lets you kind of glue together multiple objects, so you can produce many argument functions, and also glue together the outputs, so you get many value functions. And that gives you a string diagram, which is just a DAG. Or, I mean, there are versions of it where you can have cycles, but they're a bit more complicated.
What's the relationship between that DAG and a token event graph? where the functions are the events.
Well, I mean, there is a one-to-one correspondence between monoidal string diagrams and well, multi-way systems, which are themselves just representable as token event graphs. Again, this has been explored in previous
Some detail, right?
Yeah. And then so hypergraph categories and therefore hypergraph string diagrams are in turn generalizations of those kinds of monoidal categories, where now you can have an output of a single sub-expression appear in multiple sort of potentially hierarchically nested super expressions. And so now your edges are not edges anymore, they become hyper edges.
Wait a minute, wait. So you're saying, okay, so in one way to think about the evaluation of an expression is to work up from the bottom of the tree, and you keep on having these merges where arguments of functions become values of functions.
Right.
And functions have a single output value.
Right.
Now you can, yeah.
But now imagine you've got the case, which is again like a generalization of the many valued case, where you've got f of xy is a sub-expression of some larger thing.
Yes.
That uses f of xy as an argument somewhere.
Yes.
But then there's a super expression of that which also uses the same f of xy. That's not permitted in an ordinary expression tree. It's not even permitted in an ordinary string diagram, but it would be permitted in a hypergraph string diagram, because now you've got your now you've got an edge which has you have two hyper edges. You've got one that's that's got x, f, and some future thing all in one edge, and y, f, and some future thing all in one edge.
Right. So you're saying that one possibility is that f and x and y, which are sort of atoms, can appear at nodes of this thing, but you would also like it to be the case that a whole sub-expression can be a node. Is that right?
Well, no. Again, that already happens in expression trees, effectively, right? Once you've got the subtree for fxy, then wherever f goes, it represents fxy.
Yes. Okay. All right.
Right.
So what's the new thing?
Expression tree.
Sorry, say that again. What's the new case?
So you get the difference between an expression tree and an expression DAG, right?
Yes. I mean, one has shared common sub-expressions that are being represented as single nodes, and the other has them unrolled as different tree elements.
No. So even in the case where they're unrolled, there's a generalization of what it means to be an expression, which is what a string diagram, which is what.
Okay. Which is your thing, where you have different values, where you have your f1 and f2 as different outputs from the function.
Right. So in the ordinary expression tree case, you just have a three vertex, two edge tree where you've got f, x, and y. But in the two argument case, you've now got an x and a y coming into a node, and then an f1 and f2 coming out of that node. So it's no longer a tree; it's a directed acyclic graph.
Yep.
But you can go a step further than that, and you could say, well, now imagine so ordinarily f will only appear as a sub-expression in one super expression, right?
What's f now? There's f1 and f2. What's f?
Yeah, I mean, f is a multi-valued function, so you can break it down.
Fine. All right, okay. So f is like the event, and it has an f1 and f2 branch coming out of it.
Sure. And so if you wanted to think about it in terms of global multi-way systems or something, then the case of hypergraph categories would correspond to one in which a single event can causally influence more than one future event. But in the way it's normally thought of in the sort of formalism of this stuff, so a hypergraph category would correspond to one in which f can appear as the same f can appear as a sub-expression in multiple super expressions.
Okay. Why isn't that a common sub-expression story?
Well, no, so the common sub-expression is one where it appears in one super expression, and then there's sort of nesting. Right?
Okay.
But now imagine the f could appear in two sub-expressions that are not nested. They're not related. It's just the same f appearing in two places.
They're branchially related, but
right.
not, okay,
right.
But not time-like related.
Or tree-like related or whatever.
Right.
Yeah. So that would be a hypergraph category, because now your string diagram is not a DAG anymore. It's now one.
Yeah, I get it.
Now, wait, I'd like to, I have another question about what we were discussing before in terms of observer theory. So if I understand, Jonathan, what you're saying, we can meta model observers more generally by, instead of thinking about, say, axioms that we're including in some entailment cone in the meta mathematics case, we can just consider generally that observers have, certain completion rules that they're applying to some multi-computation in order to coarse grain. Problem is, as Stephen said before, this is sometimes described as, how did Stephen put it? He said, we have a multi-computation, and how exactly you coarse grain depends on what exactly the observer wants to extract from the overall system, more or less, right? Maybe the observer wants to extract some kind of bulk or aggregate property from the system, and they're going to apply some sort of completion rule in order to do so. But the difficulty is, especially if multi-computational irreducibility is at play, where you don't exactly know what kind of merging behavior you're going to get, you can't really say beforehand what kind of completion rules you're going to apply, right? It could be the case that there's some behavior and you say, okay, here's an opportunity to perform this kind of completion. I'm going to introduce this kind of rule. And then the behavior is more complex than you expect it to be. And you think, okay, well, let's introduce this completion rule. The trouble is the observer is going to be bounded to some extent. You can't just introduce, some large number of completion rules. So we're saying, you introduce, the observer is going to coarse grain to the degree that they want to. The
observer has what they have. I mean, the observer is some measuring device or us or whatever else, and we have a certain bag of tricks, and those are what we get to use.
Right. So the evolution of human technological progress is in some sense that we're slowly able to add completion rules to the way that we're, but that's not something that's easily done.
No, right. I mean, that is the nature of abstraction and other such things, that we're able to say, that these things that look different could actually be treated as the same.
Well, for some time, I've wanted to understand, because we always describe observers as being computationally bounded. And I've been fishing for, some instance in which we can say, okay, here's an example of, in a meta model, how we can actually model whatever constraints are placed on the observer. And I think the fact that the observer has some limited number of completion rules is one example of a kind of observer budget that they have.
I think Jonathan wanted to make a point.
I mean, if we want to be philosophical about this, I kind of think it's the other way around, right? My position has always been that the definition of what it means to be an observer is that you are a computationally bounded entity within some multi-way system.
Yeah.
And the notion of observation emerges as a consequence of the fact that you have to impose equivalence relations if you're going to make sense of what's actually going on.
Yes.
Right? So it's not that the number of completion rules is somehow a budget for our observation. It's the completion rules are a necessity as a consequence of a pre-existing budget that comes from computational boundedness. I kind of feel like this is...
Well, I mean, that has a very practical consequence. But which of those is right? Which view of those is right? I suspect that it meets somewhere in the middle. That is...
right.
That we have, in our eyes or whatever, we are aggregating, photons hitting different photoreceptors and so on. And we're also, and that's the sense in which we have a certain, right, but also we're not capable of having, we only have a certain budget of, okay, think about it this way. We have, 10 million fibers in our optic nerve or something. That's the total amount of stuff we can deliver from the eye to the brain. But now, so that's our kind of limit. That's Jonathan's version of, we only have a bounded amount of stuff that we can be dealing with.
Well, our bounds go in two ways, right? One is there's a certain degree of rarefication that we can achieve, but we can use instruments to be able to achieve some kind of verification that we don't usually have because we're bounded. There's also abstractions where it takes a certain amount of computational effort to coarse grain more than we would naturally. So I think the default state is we're in some kind of mediocre middle. We could get a more granular degree of resolution that requires some work. We could get a more abstract view that also requires some work to go in either direction, I think.
But I kind of feel as though that although there may be sociological reasons to make that distinction, I don't think there are any particularly fundamental reasons to make that distinction. I kind of view them as being both parts of the same thing, that both in the natural measurement that we kind of have to do, that's evolutionarily imposed, and in the induced measurement that comes about from greater levels of abstraction or thinking, improved thinking tools or better measurement apparatus, they're both a consequence of wanting to basically take the kind of wild, untamed computation that occurs naturally and turn it into something that's kind of entrained and tailored to specific human purposes, right?
I agree, but what I had it's not a sociological distinction. It's trying to understand. You have some observer. If the observer is doing additional work to change the kind of observations that they perform, trying to understand what this means in terms of adding or maybe even removing rules. I mean, if you're getting a more granular picture, maybe that involves actually removing some rule, and maybe achieving greater abstraction involves adding more. I'm not exactly sure how this works, but the point is that an observer might be interested in doing both. I'm not trying to create sociological or philosophical categories, but I'm trying to think about how we're going to meta model the observers with respect to these completion rules.
Well, we've got a very practical point here, which is in Nick's formalism, if we are going to try to prevent it from just exponentially, trivially blowing up, we have to have some kind of conflation process.
Yes.
Parameterizing that conflation process in terms of completion rules seems like a possible thing to do. In other words, one could imagine, Nick, does that make any sense to you? I mean, so in other words, if you say, so you're giving a certain set of rules. I'm a little bit.
I don't agree that those rules should be somehow external to the multi-way system. It's the observer is a part of the evolution itself. It's somehow computationally intrinsic. Those rules are intrinsic to the computation. So we never done some.
I know, but what you're peeling off, I mean, let's take this example here. What you're going to peel off is a picture of this. It might have started as a tree, but what you peel out of it is the coarse-grained equivalenced thing that has only numbers at nodes and isn't a tree.
Yeah, but peeling off that mean the computation that happens inside of the observer.
Yes, that's right.
His reconstruction of the multi-way system as it sees it after the conflation that.
Exactly. But my point is that as a practical matter, in using this as a practical computational tool, we're going to have to do internal conflation, because otherwise the thing's just going to blow. I mean, look, the universe, one of the things we have to come to terms with is the universe is just an outrageous, profligate waster of computation. We can think of it as treeing out all these things. There's no equivalencing going on. It's just spewing out different possibilities.
Sure.
Right? But we, as observers of that, are doing all these conflations, and our useful models of the universe do involve mergings. I mean, in some intrinsic ontological something or other sense, maybe the universe isn't merging at all. It's just that with respect to any of our experiences of the universe, it is merging. And my point is, how deep do you put that merging inside the computational process that you're doing to, do multi-type stuff? Because if you keep the merging only at the edge, to use a different analogy from computation, if merging is only at the edge, there's an awful lot of stuff that has to happen in the middle. So the issue would be to move merging away from the edge and into the interior.
Right.
And then the question is, to parameterize that, I think that moving merging away from the edge and into the interior is deeply entangled. I don't mean that in a literal sense, with traversal orders and foliations and things like this. Because, defining a foliation, it doesn't make any difference. If all you're doing is the interior, you don't care what the foliations are. You just do what you do, and eventually you'll do everything and so on. There's no, but foliations become important when you want to have waypoints. And the confusing part about the whole thing is that our experience of the universe is based on those waypoints. It's not an input-output experience. It's a, journey type experience. So, again, we're pushed back into realizing that, I think we should look at some particular parameterizations. And I claim that this is deeply related to the thing I keep on yakking about of, probabilistic programming versus logic programming versus whatever else. These are all, as an efficiency hack, okay, every one of those could be done on the edge. But as an efficiency hack, they also need to be done in the interior, I claim. In other words, it could be the case that everything is lazy right up to the point where you're on the edge and you're doing a measurement. But in fact, for practicality, and that's related to, back in the, I don't really know this stuff very well, in logic programming, cuts and all this kind of thing. I don't really know how those work. But this concept that you don't just tree everything out. I like theorem provers as well. Same story.
Right. The thing that James was talking about earlier about how there was some fundamental irreconcilability between, the gluing things at the edge versus gluing things at the intermediate, that just doesn't exist when you're, say, traversing a proof tree, right? The way that something like Vampire, the way that it traverses proof trees is it will go, until you get a critical pair resolution, and effectively until you get a branch pair resolution, and then it will just equivalence out all branches that led to that branch pair resolution. So it's kind of doing retrospective state equivalence based on, future, essentially intersection of entailment cones. This is a fairly standard idea.
Mm-hmm. But so your point is the equivalence of observation on the edge to observation in the interior. There is presumably a calculus of what types of observation on the edge can be interiorized. It's not self-evident what you can do. You could imagine a measurement on the edge that was not interiorizable. Right.
This, in a slightly modified form, this is a fairly central question in categorical quantum information theory, because essentially this distinction of whether you do treeing out, whether you do pure treeing or whether you have equivalences is really the distinction of whether the tensor product structure on these, if you think of these now as string diagrams, whether the tensor product structure is purely Cartesian or whether it's some deviation from a pure Cartesian tensor. It's more like a Kronecker product. And so then, in effect, what the question about, do you do equivalencing on the edge versus on the interior becomes the question of you've got some very complicated looking Cartesian product in some SMC, and you want to say, well, can I turn this into a?
Sorry, what's an SMC?
Symmetric monodal category, the setting for.
Yep.
And so, and you want to ask, can I turn this into some very complicated looking Kronecker style tensor product with certain properties? And then there are cases in which you can do that, and there are cases in which you can't. And what that translates to is, can I glue the vertices of this diagram together in such a way that I obtain a tensor product structure with these axioms satisfied?
Right, and I think in terms of language of releology / meta modeling, Stephen, is the point you can't do it. You can, if it's the case that you can only do a measurement on the edge, so to speak, it's because the multi-computation was sufficiently multi-computationally irreducible that you weren't able to make any equivalences up until.
Yeah, that's a good way to put it. That's you've been pushing this idea, James, of multi-computational irreducibility, which is, and that's, I think this is a good case of it. That is, can you, a reduction is, can you go from the edge into the interior? If you cannot, it's a sign of multi-computational irreducibility.
Right, and there might very well be a nice category theory way of
which is what Jonathan's saying. One is a Cartesian product that is that you have that, and it's only modding out happens after the fact, and the other is which you can write it as incrementally. You can write it as something which isn't a Cartesian product and already has that equivalencing happening.
Right.
Which is, so that question of whether, so what's an elementary mathematical example of this? Of where you have things and they're producting out, and then at the end, I mean, there's got to be some example just with numbers, where you just say, at the end, like for example, a random example. I don't know why this one comes to mind. You remember that tropical algebra thing? I think, Jonathan, I think you were working with some student.
Yep. It was Anjali's project from 2018 or something. Yeah.
Right. I mean, which is, remind me that's where instead of taking
you've got a max plus algebra, right? So you produce a semi-ring where your addition operation is the max operation and your multiplication operation is ordinary addition.
Right. I have no idea why it's called tropical, but let's not worry about that.
Because one of the people who developed it lived in Brazil.
Okay, fine. That's terrific. Okay, that's useful. Okay. So anyway, but is that a case where, again, I can imagine something where you do a computation with numbers and then you're maxing things out at the end, but there isn't a way to sort of, actually, here's an example. So if you do with mod numbers and you're doing ordinary arithmetic, it doesn't matter whether you work with a finite field and you do that all the way through the computation, or whether you compute with huge numbers in the intermediate stages and then at the end you mod it out. Did that make any sense? I mean, if I take, just some random computation, okay? If I take
homomorphism.
What's that?
It's a group homomorphism.
Yes, probably. I don't know. Let's say I do this and I'm okay, and I go 10 steps here, right? And I've got big numbers, and now I say mod that, comma 11. Okay, I've got my numbers there. Now that's, in this particular case, that is equivalent to just saying, he says, not actually knowing whether it's true, but I think it's true, isn't it? Yeah, that's true. But that's not always true for for some measurement operations like this would not be internalizable in this way. Is that right? I mean, like I was thinking this tropical case might be, maybe it isn't, I don't know. But there's plenty of things I could do here. Like I could say, I don't know, what's the, how many prime factors do these numbers have? There's no way I can internalize that in this way. I think this is fairly obvious.
Right. But doing mod 11 is a homomorphism from the additive group of the integers to the cyclic group.
Okay. Okay, so you're claiming there's some homomorphism. It's a commuting of operators in some way.
Do you apply the mod before you do the addition in the first group?
Right.
Or do you apply the mod to
Okay, that's practically the definition of a homomorphism. Yes, okay, I get it. Right. Well, okay. There's more to understand here, and I'm unbelievably late for something else. So we probably should wrap. But Nick, the great work in this idea about hypergraph compilation. This looks very fertile, and I think we are, lots of things are converging here. And I think the thing that to Christopher's point about the practicality of doing this as a practical evaluation scheme, we're not there yet. We need to explore this with respect to specific functions like, replacement rules and so on, and see how that works. And it will be good to, there's clearly, I really think it's worthwhile to start parameterizing these kind of measurement operators or whatever you call them, and just see how internalizable some of those things are and how much they can, increase the efficiency of what Nick is doing, which otherwise we're going to have a problem with, because treeing things out is ultimately not efficient. So the question is, even if it's a theorem proving, way of doing it, like Jonathan's comment about vampire, eating its way back up that must be somewhat similar to many of these theorem proving. In the end, with most theorem proving, you're working from the answer. You know, you got a giant treeing out that could happen, but in the end, you know what the answer is, and you're going to find the proof. You're going to be working backwards from the answer. Anyway, okay, I have to run, but this was great. Thanks, everybody.
Yeah. Thanks,
And